All right, hello everybody, and welcome to the next compiler demo. It's only been 2 weeks since the last one because I wanted to plow ahead and get some new features done, simply because it had been many months when I was not really able to do anything on this because I was working on a video game. So, quite some time ago, in a demo some months ago, we introduced polymorphism for procedures, so you could pass various argument types to the procedure, and the procedure would be recompiled to deal with those, right? It's sort of the equivalent here of templates in C++ or whatever. But that was only for procedures. It wasn't for data structures at all. So today, we're going to start doing that stuff to data structures. And this is going to be sort of a part 1 of 2, or maybe even 3. So today we're going to start doing data structures that have parameters, but we're only going to deal with value parameters and not type parameters. There's not necessarily anything harder about type parameters. In fact, most of the infrastructure for type parameters would just work because of what we're doing for value parameters. However, there are some interesting decisions that start coming up. There's some interesting, basically part 2 of this is going to be some interesting new things about how you keep code bloat down and combinatoric explosion from happening when you start using a lot of templated parameterized things. And I have some thoughts on that, but they're not 100% solidified. So what I'm doing this week is I'm going to do everything up until well, we're just going to do the basics. I'm going to stop rambling. I'm going to say we're going to do the basics. It'll be obvious by the time we're done. And then we can cover some things in Q&A. So it always seems to me that if you want to do parameterized data structures, and if you are interested in video games, you want to do the kind of math that we do all the times. So I decided to start with a basic vector, right? This is, if you're C++ brainwashed or one of those languages that comes from that, you might think vector means like an array of things, but it doesn't. A vector is a mathematical object that's closed under addition and scalar multiplication. If your programming language is not like C++ and does not pathologically name everything the wrong thing, then you would know this. We're just going to make an n-dimensional vector, right? So instead of, prior to today, you would just have a struct, right? And you would have some members in the struct. And as of today, you can have parameters to your struct. And here we've got one parameter, n. It's a signed 64-bit number. We might not care that much about the size. We might say int here, which means, remember that int is specified to be signed 64-bit anyway, but int might just mean we don't care. It's a way of saying we don't care. Anyway, so what happens is a vector has some array of floats called C, and the length of that array will change based on what the n is that you pass. Now, this is a compile time thing. This is not a runtime thing, right? So some languages will give you types that you can adjust at runtime and that are squishy and stuff. But this is a this is a language that is fast because all that stuff is decided at compile time, and that you cannot change it at runtime. So when we construct a vector with parameters, it is going to be an action that happens at compile time, right? Just to be clear about that. Let's just look very simply. So today's program, as always, does a bunch of stuff, and it's doing it at compile time. Okay, so I'm going to run this and pipe it through more so we can just see. So we start out and we just do some vector stuff, and we're printing vectors of various dimensions. So we've got a 3D vector, and we're taking the length of it, which is 5, which you know because it's like a 3, 4, 5 triangle there. Here's a 4D vector, right? And then we can normalize it and dot product it with itself and all that. So let's go look at how that happens, right? There's nothing too surprising here, except that if you were to do this in C++, it would be a lot more painful. Let me make sure that runs to completion. There's a subtle reason why I wanted to make sure that runs to completion. Okay, so if we go to this thing called vector stuff, this is our code where we use it. And we're just saying v3 is vector of 3, v4 is vector of 4. It looks like a procedure call, except it goes in the type slot. Like, remember, we also would be able to assign a value here if we wanted to. But this is just saying v3 is of type vector of 3, v4 is of type vector of 4. I'm filling out the components of v3, right? I'm printing them. That's where this comes from, right? I'm just saying for each component of v3.c, print that, right? New line, take the length, new line. All right, so length is a procedure that we're calling that's taking a vector, and it's taking different vectors. So here's the length of a vector 3, here's the length of a vector 4. So let's go look at that, right? Now, as we have seen previously, this is a polymorphic function. It takes a parameter that we're naming t, and it's a type variable, so we use this $sign just to say it's a variable, right? And it returns float 32. And to remind you guys of all the features that we have available when you call a polymorphic function like this, I have this is a vector up here, where we basically get the type info for that, for whatever t the user passes, and we can inspect it. We can make sure it's a struct. We can make sure it's a struct that's derived polymorphically from the base vector, right? That is one way of type checking things that is arbitrarily specific, but we don't actually need to do that, right? So first of all, we could not do this at all, and then as long as we always called length correctly, we would be fine, right? If we didn't call length correctly, we would get an error message down here somewhere. But the whole idea behind C++ concepts and stuff like that is that sometimes you want to intercept things, intercept problems, you know, at the calling site so that they're easier to track down, right? And this is nothing new. You know, we demoed all this several months ago, possibly even a year ago. Now, the thing that I've added for this time is that it just turns out that very often you want a simple type check on a general kind of a type. Like, so we're going to have this thing called vector, and we're going to instantiate different kinds of vectors of different dimensions. And when we say length, we don't care which vector it is, but we want it to be one of those. And I've just made a little notation for that. So here's a vector add function, where we say we take a $t, and then the slash means, oh, and it's a vector. And the slash is not, you know, that's temporary syntax, just like everything. Don't take it too seriously. It doesn't mean divided by. It just means slash. Like, we have some type t, it's a vector. So if you get that wrong, then it'll complain. So let's just trigger that first of all. So let's go down to vector stuff, and I'm going to say len is equal to length of hello, right? So that is not going to be liked. Oh wait, redeclaration of len. That's other len is length of hello, right? So this is our error message. Argument is not a vector, right? That's being printed out up here, line 24. Argument is not a vector, right? But instead of having all the, so I just brought this up to remind you of how much detail you can go into when you want to type check something. You can literally do anything, but instead of doing that, we can also just do this, right? And then the error that we'll get is compiler generated rather than generated by us, right? Oh, and here it says, well, the type we're passing in is not a struct, right? If it is a struct, let's pick a struct. Foo. Do I have a foo in this? I do have a foo. Bar. So this looks kind of like a vector, right? But it's not a vector, so don't complain, right? What? I need to declare a bar. Okay. So type restriction doesn't match. We wanted a vector. The given argument is a bar. So this is exactly the kind of thing that C++ concepts is trying to do very badly, very confusingly, but you get good error messages from the compiler. Now again, this slash check thing is it's very simplistic, but a lot of the time you want a very simplistic thing. If you want the more complicated thing, you write a procedure. And the procedures usually don't have to be this long, because once you have some utility functions, you can just call them very quickly. All right, so here we have a few examples, and they're all very straightforward. Well, let's go back to length for a second, right? We just have some sum, and we're iterating over all the components, and we're adding the square of each component to sum, and then we're returning the square root of that. Anyone who knows vector math should be very familiar with that. Someone's asking about duck typing. We're going to talk about duck typing later. What we're doing right now is not duck typing. This is strong typing. It's different. You can have duck typing just fine if you want to. And here's a bunch of procedures in that same spirit, or functions these are, right? So we want to add two vectors, right? So we're saying the first one is of type t, it's a vector, and the second one should match that. And then we just add all the components in a loop, right, and return the result. We're going to dot product two vectors. Again, they're the same type. If their dimensions don't match, then those types will mismatch, right? So these are all very simple. And then, of course, we can normalize a vector. This time it's a pointer to that same type, and then we can change it. I like saying stuff like normalize or 0, because remember, normalize is not defined if your vector is of 0 length. And so the question is, what do you do? A lot of people have a function called normalize or a procedure called normalize where they just, either they 0 it or set it to a default vector if it's 0. I prefer to put that explicitly in the name because then it encourages you every time you're normalizing to think about what you want to happen and make sure that you're making the right thing happen. Okay, so this is very simple so far. It's nothing too exciting. This is just to introduce the idea that structs have parameters. We're going to get to the exciting stuff soon. All right, this foo down here was to demo exactly what I was talking about, is that you can't pass a foo. I literally retyped what this foo was. So yeah, this is for strict type checking, this slash notation on things, right? If you want duck typing, which you certainly can have, then first of all, maybe you don't type check at all, because like I said, if you don't check this, in fact, let's do this. Let's delete the slash vector, right? Well, actually, let's keep it for a second. Let's go back down to the foo. We'll say foo length is length of foo, print foo length is. Right, so we're going to do that. This will not work, right, because we're type checking and we're preventing it from happening, right? So it's saying, hey, we wanted a vector to give, oh, because I've got my bar thing still. Let me get rid of that so that we get down to the foo at the bottom. All right, so now we're giving it a foo and it wanted a vector, right? So if we take that out, then you do get duck typing by default. I didn't try this, so I hope it works, right? Yeah, it worked. So let's scroll back up to here. Where was it? Foo length, oh, because we didn't set any components. For foo.c, we're just going to set all the components to 1, so it has a non-zero length. Whoops. Yeah. Parsing. All right. Foo.length is 2 dot something, right? So you get duck typing automatically from a polymorphic procedure like that. The thing is that when you do that, if you don't pass it quite the right thing, then your error messages in the middle might not be as nice as you want. So if you want to have duck typing, you can write a procedure like this. It just compares the members of the struct that you pass in versus the members in some target struct and makes sure that they match. Now, what does match mean? It sort of depends, right? Maybe you want the types to be exactly the same. Maybe like if someone has an array of floats and you wanted an array of doubles, that's still good enough for that particular procedure. That starts to become something that the programmer of the application decides. So we might provide some duck typing comparison checking in the standard library that you can just call to get that. The question is just like what type checking modes are going to be useful for people. Right? Obviously, you can do completely strict, but then beyond that, what do you do? Anyway, so a bit of a diversion, but there you go. Let's put this back. So that was the vector stuff. We're still not really doing anything that interesting yet. We'll get there. Now, to get to the interesting part, I needed to implement another feature, which is that we have array literals in the language now. And again, the syntax for this is temporary, so don't take it too seriously. But basically, you can use curly braces to designate an array literal, right? And you say what type it is, and then you put the stuff here. Some languages don't have a type that goes here, and they just let you do this, which is fine until you one day add that in the middle, and then the type of your whole array changes because you typed something that has a decimal point. I don't like that policy. I also don't necessarily like this because it's too verbose. So I think in the future what we might do is we might run the default type inference on the first item of the array, right? Which for this case would be 64-bit integer, and then extrapolate that to the whole array, and then complain if you don't match that, right? So for example, if you just do something like this, x equals 1, that's valid in this language, right? You don't have to suffix this type, and the compiler has to decide what type that is. And eventually it figures out, oh yeah, there's no constraints on it, right? Like if you had done this, that's valid, but you didn't do that. So it's like it has to decide what type that is, and there's some basic rules that determine what type it is, and it turns out to be 64-bit integer. So I feel like the right thing to do is to run that on the first element, right? So you'd get 64-bit in here, string here. But because array literals were not the feature that I'm demoing this time, I didn't put that much work into them. So I put in a thing where you declare the type here. Now, why would you even want to do that? Well, it's because then this can be more of a value, right? Like in C and C++, array literals are not really values. They rely on context to have meaning. So you have to have something of a specific type on the left equals open brace and some stuff, right? You can't do, for example, what I'm doing down here, or I do like a for loop and then there's just an array value and we're iterating over that, right? Or you can't just pass one of these as an argument to a procedure in C, right? So I want you to be able to do that, which means it has to sort of be a value on its own, which is why I'm giving it explicitly demarcated types right now. But later those will probably go away unless, I mean, you'll probably always be able to say them if you want, right? But anyway, this is not that big of a surprise. We're just saying, hey, this is an array of floats. We're iterating, we're printing them, right? So this is this part down here. F 0, 1, 2, 3, 4, 5. And then S is 0, 1, 2, 3, right? We're printing out each of these. And then I've got this concatenate procedure and I'm spreading S. So I'm just showing that this spread operator that operates on arrays works just fine on these, in fact, because this casts implicitly to an array. So, you know, we're concatenating all that and putting it into a string called together, which we're printing here. That's hello sailor. So this is all basically what you would expect. And then we can iterate, like I said. So you can go, and this syntax will be a lot more convenient when you can omit the type thing, because just saying something like 4149 that's pretty convenient, right? But here we're just saying, let's make sure these are all U16 so that when we print the size, it had better be 2 bytes, which it is. Size of 149 is 2 bytes. And then S64, so the size all had better be 8 bytes, and it is. Okay. So again, that's just a feature that we're going to use to do the interesting part. And there's another feature that we're going to use to do the interesting part, which is this thing called place, which is also a low-level thing that I did because I wanted the ability to do something like a union, right? So unions in C and C++ are ways that you put members of a struct overlapping each other in memory. And they're a relatively like high-level way of doing that that's trying to be safe. I decided to do a quick and dirty thing that is less safe. In retrospect, it wasn't really any less work than doing a union, so maybe I should have done a union. But I'm just going to explain how it works. This is, again, not necessarily something that I'm viewing as the way it's going to work long term. It's just something I wanted to do. Like I put it together in a couple hours just to do the rest of this demo, right? But anyway, so what happens is I've got this struct foo. It's got 4 floats, no big deal. Then I'm saying place to F0, and what this does is it kind of moves this memory cursor of where the next item is going to go in memory up to F0, right? And then we have C, which is 4 floats. So C's 4 floats are going to be on top of all of these, right? So this is going to be the same as saying in C, union And then I think you would have to do this. I'm not going to write the type, but well. And then you can't really have an unnamed struct, so you can't, I don't know, there's probably a way to make this happen, right? But switching back and forth is, so whatever this would be in C now, it's something like this, right? So we're doing that, but we're doing it in this more, little bit lower level way. You can imagine, though, that if you're generating structures with code, which is what we're going to do in a bit, that this is maybe an easier way to do that, to do things when you're generating code. If you say place without an identifier, then it'll skip back to the bottom, right? So you can go up, write some things, and go back to the bottom. Here, I've got another array literal. This one is constant, though, so it doesn't take up any storage in this struct, right? So in this little place test, we make a foo. We're assigning, we've got values from 9, 8, 7, 6, right? We're assigning 9 and 7 with the names up here, and we're assigning 8 and 6, click. We're assigning 8 and 6 through this array, but we should just get 9, 8, 7, 6. I'm going to print out the whole struct so you can see everything. Then I'm going to print out the size, right? And the size should be the same as the size of 4 floats, because these two things should overlap, and this thing should not take storage. So when we do that, right, so here's the result. F0 is 9, F1 is 8, F2 is 7, F3 is 6. So this did successfully overlap that. And then the size is 16, which is what you get when you have 4 32-bit floats packed together. So that's all fine. Now we get to the point of this talk, which is the matrix stuff. Matrix stuff, this makes me happy. Okay, so that vector class that we introduced that has one parameter was interesting enough, a little bit, but I wanted to do something that is really painful and close to impossible, or completely impossible if you take into account like user experience, programmer experience in C++ to do this well. So suppose I want to make a linear algebra library, right? So I've got matrices and vectors flying around, and I want it to be efficient at computation, right? So with some types of matrices, you might know some things about them, like this matrix is just a diagonal matrix, right? Or this matrix is the identity except with one column vector swapped in, or something like that, right? So you might have a matrix plus some knowledge about which elements of the matrix are populated. And then you may want to use that to do fast computations, right? So suppose I want to multiply two 4x4 matrices together. That's a lot of multiplies and adds by default, but if you happen to know one of those is diagonal, it's a lot faster, right? Because you do many fewer computations, because all those 0 elements that are off diagonal kill many of the terms, right? So how do we codify that and do that at compile time? Well, I will show you. So here we've got some matrix called M. It's a 4x4 matrix, and it's got this flags field, which I'll show you in a second. Let me show you that now. So matrix is a struct. It takes 3 arguments, an M, an N, and a mask. The mask tells us which fields of the matrix can be populated, which fields are present in the structure. And we're going to generate a new structure for each type. So as we know how much storage a matrix occupies, it's going to take more or less space and more or less computation, right? Now, instead of defining, remember up when we did our vector, we just gave the body of the struct and it used the parameter here, right? For the body of our matrix, we're actually going to generate it procedurally, and that's what this body text thing does. You may remember that from before. Matrix stuff. You may remember body text from before. We've greatly streamlined the notation. Oh, also, there was a thing with body text and modify before where you kind of had to match the names of parameters, and that was a little weird. And in retrospect, it wasn't really necessary. So all this works way more like regular code now. So now body text, you don't have to type a procedure necessarily. You just open a scope and you get all these variables defined as parameters inside here. And in fact, just like with a modify proc, you can modify them by assigning them to new values. I don't think we do that here, but we'll do that soon. So we want to generate a string for a matrix. And you know what? Before I go through this and try to make too much sense of it, well, okay, let's start glancing at it so that we know what's going on. Then I'll show you something cool, right? So we're going to generate a string that represents the body of this struct. And then we're going to feed that back into the program to be compiled. And what do? Well, we iterate over all the dimensions, m first and then n. M by n is a common way of referring to the dimensions of a matrix. And then we ask, is this bit set in the mask, right? In other words, do we want this component? If we do, then we add whatever body that we've outputted so far, which at the beginning is just going to be space, right? Because I want to indent. You'll see why I want to indent in a bit. You might think, oh, it's auto-generated code. Why do you care about indentation? But you do. So I put the indentation or whatever we've outputted so far, and then my names are just going to be like underscore m underscore n, right? So I'm outputting the m and the n, right? Actually, so everything we've output so far is the body. This is the spot where we put the comma, right? The comma starts as indentation, but then after the first element, we put a comma because we're making a list of struct members, right? Blah, 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 and then we keep building up this string. And so what we're building, I will show you. Because as of now, anytime you generate a string and add it to your program, then for debugging purposes, it gets added to this file called added strings, right? This is called W1 for workspace 1. As you might have noticed in a previous demo, you can generate multiple workspaces, in which case this will go to multiple files. So here you can see everything that was generated by the program, and in fact, for debugging purposes, any code that you generate via a string like this will be referred to as though it were coming from this file. So that if you generate an error and the debugger has to point at it, you'll get something that you're able to browse through in the debugger and understand, right? So that first matrix instantiation that I called with 44 and 08421, this is the struct that we generate, right? So we're going to output an array of 4 floats because 1248 only has 4 bits set. Then we're going to generate 4 members, right, which is what this is doing. And then we're going to generate a bunch of indices, which is a mapping from, if I only thought this was a 4x4 matrix that was dense, then I can look in here, and if the member is -1, it means it doesn't exist. Otherwise, it gives me the index into this array of that element. So you can write things that iterate over the dimensions of the array and map back to the members, but you have dense storage for the members, right? So now let me demonstrate something. So you might think, oh, this is auto-generated code. It's really hard to debug. What if I make a typo in here, right? That's excessive. But what if I make a typo? What happens? Well, oh, I still got my foo. Got my duck typing foo. Let's get rid of that again. All right. So we got a semicolon expected. Who knows? Oh, well, here, right? And it's in added strings, line 9. So we can go to added strings, go to line 9, and there it is, right? There's our problem. And we even get a little visual output of the problem now, right? So compare this to error messages that you get from C++ templates, which are insane, right? But this should be a way harder problem because this doesn't even ever exist in this program source, right? But it's apparently not that hard if you actually care and try to make the messages nice, right? So now I should point out this added strings file is not necessary. In fact, if you're trying to make a fast compilation, you might even turn this off because you know, when you add strings to your program, you don't have to hit the disk in order to add those strings, basically, right? This is just a debugging aid and understanding what's happening in your program aid, right? So I'm going to delete my error here, and then I'm going to rerun this. And that all works, and then we go back here, and do I have Emacs set to auto load? Yeah. So that's all good. So let me show you some things about this so far. So M is a particular matrix with particular dimensions and particular flags. If I change the flags or the dimensions, I have a different layout and a different type, right? Oh, let me say this init to counting coefficients is just something that goes over this C array and sets the elements to, I think, 1, 2, 3, 4, right? However many elements are in there, it just fills them up. So if I go back here, M is, here I'm printing out the entire struct. It's got a 1, 1 that's 1, a 2, 2 that's 2, a 3, 3 that's 3, and a 4, 4 that's 4. And then we're printing it out here. Let me show you this print matrix. Because this is doing what I was talking about before. It's saying, OK, the dimensions are m by n. It's just printing that. And then it's just doing a dumb 2D loop over the m and the n of that particular type, right? This is using that slash notation saying it's some kind of matrix. We don't know which one. We're getting the element, right? And then we're printing an extra space if it's a small number because I didn't want to do more complicated formatting here. And then we print it. So that's what's printing out this square matrix. So we don't need to know which elements are populated if we don't care. And this get thing is just checking that matrix index, right? Or, sorry, it's getting a linear index from the two-dimensional size of the array. That's what matrix index is. We'll see that in a second. It's trivial. Packed index is the index into this, right? So we subscript this by any number between 0 and 15. So this is a 4 by 4 array, right? So we subscript this. Well, see, if that's -1, it means that element of the array is not populated. So let's return 0. Otherwise, let's return C sub whatever index, right? So if we get this one, it's C sub 0. If we get this one, it's C sub 2, C sub 3, whatever, right? And so this matrix index, if you program, you've seen this kind of thing a zillion times, right? We're just getting the indices in m and n, and then the n element of the array, and we're multiplying by that and adding. Because in math, these are often 1-based, I'm using 1-based indices for the matrix all through here, which is why I'm subtracting 1. Okay. So what the rest of this body of code is doing is just generating these other elements, right? So this is generating those names. This is generating that coefficients array that's here. And this is generating that indices array that's here. It's very simple code. It's not rocket science at all. It's just like things that you write a million times. But all of a sudden, it's doing cool metaprogramming. All right. So anytime I have a new installation of Emacs, I'm always off. All right. So that's instantiating a basic matrix, right? If I make another matrix with the same coefficients, it's the same type. I don't generate any new code. The compiler knows that this and this is the same, even if it happens in different files, because we don't have compilation unit problems like C and C++ have, right? So these two things are always the same type, right? So I can assign M to M2, and that just works. We're not going to bother looking at that. You just get another copy of the same matrix. Now, this kind of passing arguments to a struct uses all the features that passing arguments to a procedure uses. So you can pass them in an opposite order and use names or whatever, right? So here I'm passing mask first. Let me go back to the definition of matrix just so you can see. So the arguments go m, n, mask, but here I'm passing mask, m, n, right? And they're still the same type. That doesn't confuse anything, right? So m and m3 are still the same type. Now, I have this other thing called diagonal matrix, which is a convenience type. Like, say I'm making diagonals all the time, and I just want to say, oh, it's a diagonal matrix of 4 dimensions, right? Well, that only takes one argument, and it generates a body text that's much simpler. It figures out what mask we need for that matrix, and then it makes a square matrix with that dimension twice and that mask, and then just usings that, right? So let's, if you remember using, right, it's basically the thing that gives you struct inheritance. So I can make a type called diagonal matrix, and it just makes this same kind of matrix on the inside. I already made that, so the compiler doesn't need to do anything else. It knows that it's this up here. Because it knows that it's that, let's go back and, so A is diagonal matrix, and M is a member inside it matrix with all these same components. Now, A dot M is the same type as this original matrix that we made back here, because remember the flags and dimensions are the same, so the types are compatible. And because we have auto coercion with anything you're using, I can even say that M equals A, whereas even though A is a diagonal matrix and M is a matrix, and all that just works. Just does what you want, right? And that's not because they duck type to the same, it's because they strongly type to the same, right? So again, it's worth understanding the difference. All right, now we're going to do a matrix of a different type. We're going to do another 4D matrix, but it doesn't have very many elements set, right? It's 4 by 4, but the flags are just 3. It's just got 2 elements, 1, 1, and 1, 2. And then we're going to add those, right? So let's look at the printout of that. So our matrix B just has these 2 set, and all the rest are 0. And if you look here in the struct form, it's just got 2. It's a much smaller struct, right? And we're going to add that to oh wait, we don't add that yet. All right, C, I had the add on line highlight and I was confused. So we're adding A and B and putting it in C, right? What's A? Well, A is basically the same as M. It's a diagonal that goes 1, 2, 3, 4 along the diagonal, right? So here's A. We didn't ever print A in square form, but it's 1, 2, 3, 4. Here's B. So we're adding a 1, 2, 3, 4 across the diagonal to this 1, 1. So we get 2, 1, 2, 3, 4, just like you would expect. However, we don't have to do all this math that you would do for a 4 by 4 thing, because matrix add is also generative. It says, we'll look at this in more detail in a second, but it says it takes a matrix A and a matrix B, and A and B can be different types. And it generates a matrix C, right? Which is a different type than A or B. It'll be the same dimensions, because if the dimensions don't match, then we can't add them, right? Which is what we're checking here. But if the dimensions do match, the flags are probably different. So you get a different type. Let me just go down here. So see this? A full 4 by 4 matrix add would be a lot of adds. This is only a few, because we know that C, I don't draw the parameters in this yet, by the way, but C is the result matrix, and A and B are the arguments. And we know that it's mostly just the diagonal elements of A plus these 2 elements of B. So we've generated this add procedure that is very, very small and does exactly what you want, right? How did we do that? Well, we did this, right? We loop over M, we loop over N. Let's take the bit for that coordinate in the dimensions we care about. Oh, C mask, okay. We did all this first. So you get the mask from A, you get the mask from B. If you remember way back, the type info, the runtime type info thing that we demoed way back, you have access to all that information in body text and all that, right? So we're looking up the field by name, and we're getting these masks. And then we're generating a mask for C that's ORing those together, because if you're adding 2 matrices, anything that could be non-zero in either one becomes non-zero in the result. And then I'm going to dynamically specialize a new matrix. This is a little trick that says, okay, we're allowed to make this type at sort of runtime, but really we're actually running at compile time, which is why we're allowed to make a new type. Remember, this is a pre-compiled language, so you don't go running around making new types at runtime. That would make the language very, very slow. But at compile time, you can just you can make a new type and just stick it in, right, before the program's done compiling. So that's what we do here. We make a new matrix. It's got the same dimensions as both A and B, but the mask is equal to C mask. All right? Then we go fill out the text for it and return that string, right? So the text is just all these additions in the straightforward, obvious way, right? So if the bit for whatever dimension we're operating on right now is in both, then generate a thing that says A plus B. Otherwise, if it's only in A, generate A. Otherwise, assert that it really is in B. Otherwise, our code's broken. And do a thing that says B, right? So that's why this says A plus B, and this says only B, and these say only A. So that's very nice. Here are some for trace, right? So here's trace of a diagonal matrix. It's got all 4 components. I mean, again, the code is not very crazy. It's just the same thing. In fact, these could have been factored out as oh no, this is a different check, but you could factor this into like assert that the matrix is square, because you probably a lot of the time care that your matrix is square. You'd probably have a few utility functions like assert our matrices are the same dimensions or whatever. So again, for trace, we get the mask, and then we iterate over and look at each thing along the diagonal and either generate an add or don't if that bit is present. And then if we didn't generate any adds, we return 0. So if you gave me a totally empty matrix and said, give me the trace, it would give you a function that just says return 0, which is great, right? Anyway, so here's a trace of that diagonal matrix. Here's a trace of the one that just had 2 elements, one of which was off diagonal, right? The trace only adds the elements along the diagonal. So here we just get 1 coefficient, right? So that's all good. But it gets really good when you go to multiplication. I don't know if we're going to really, I don't know if it's worth diving into the multiply code. It's a little longer, but it's basically doing the same stuff that we already did. It's the same technique, right? It's just your terms cross in a different way, so there's a little more code to generate. So here is a full matrix multiply. I'll show you where this comes from in a second, but this is what it looks like if you do a full 4x4 times another 4x4, which you would do often if you're concatenating transform matrices or whatever. Now, often in graphics, we might have like a 3x4 plus a homogeneous 1 or something, in which case you don't need to do all this. But if you know that one of your matrices is diagonal or is just a rotation matrix or something, then this can be greatly simplified, right? So here are some matrix multiplies for some other cases. This looks like that diagonal matrix plus the 1 off-diagonal element, right? So look at how much less computation that is than this. It's way less, right? Wait, I lost my place. I lost my place. Anyway, this is another matrix declaration. Yeah. Are those the only 2 multiplies I did? I did this one, which is less. Oh, this is for different dimensions because we're up to 5 here. So let's go back to the code. So that's what we generated, and let's just show what we did, right? So remember, B was our tiny guy, A was our diagonal matrix, and C is adding, right? And then we printed the traces of these guys. We multiplied A by C, right, which were 2 diagonal. Oh, C was diagonal plus 1 off diagonal, and A was diagonal, right? So we print that product, that's where that code looked from. And then dense, so -1 is like all bits lit, right? So dense is a 4x4 matrix where all bits are lit. We're going to init those coefficients again, so they're now 1 to 16. And we're going to square that matrix. We're multiplying it by itself. So that's where we got that giant thing with all the coefficients. And if we look at what that prints out, we get this, right? So that's the product of dense in itself. It's a matrix of, square elements. Or not exactly, but, you get what I'm saying. It's the matrix squared. So then just for fun, down at the bottom here, I did this stuff on some slightly different dimension stuff. So I have a 3x5 and a 5x2, right? And so when you multiply those, you're going to get 3x5 times 5x2 is going to give you 3x2, right? And just to demonstrate that that works and that you get the right type, I say just this result is 3x5 times 5x2, and we get the result, right? So here we go. We got a 3x2 matrix. That's the product of those. And that's everything I wanted to demo today. I wanted to just have a shorter demo than usual because often these go on to like an hour and a half. So doing one less than an hour seemed like a good idea. But I'm very excited about where this is going. The next thing I did, like I said, next week is going to be, not next week, but next time is going to be now type parameters. Because often in a data structure, you want types and values, right, as parameters. And then we're also going to do management of code bloat, for which there's some really good things you can do, I think. So are there any questions about what we have said so far? Is there anything I skimmed over too fast or that people want to understand better or see? Question, could I use some stack context trickery to spoof a field onto an object before it gets duck typed? Pass a float onto a function that wants a vector, but before that call, have a call. No. I mean, if you want to do that, just do that. I mean, you could cast your float to a struct. That would work. But that wouldn't be a new language feature. That would just be a thing. Like, just like in C, you can cast your stuff to other stuff, right? Yeah. In fact, it works better here than in C, because here, every single type is of a well-defined size. So you don't have this weird stuff in C where, like, I don't exactly know what size this is going to be, so it's dangerous to cast it to this other thing. No, everything is known, and so whether two things will be the same size and safe to cast is either known or it's known whether that's true, and it's either valid or not valid. It's a much simpler situation. Why is the length of the vector type not like a size t? Size t is an integer value, and vectors are real numbers. So you want a float value here, right? I mean, you're talking about length. You don't want a size t there. Length is, this is not a C++ vector that's an array of bytes, right? C++ people are the worst at naming things in the world. This is a mathematical vector. So the length of the vector is like the length of a line in space. This would have been a very confusing demo for people who don't know that. But yeah, I should have maybe made some diagrams about what vectors and matrices are, but whatever. Will the compiler optimize away the for loops for small vectors in the length add functions? That's generally something that compilers do. However, you could also, if you want, like instead of having this be a procedure with a loop in it, I could have just said body text here and made some code that just manually writes sum plus equals it times it 5 times, or just not even plus equals, just like writes it out, the sum, just the same way that I did with those matrix routines below. You could totally do that if you want, and then you don't have to worry about the compiler. You know, what is the compiler going to do? You know what you can do, right? Do I detect duplicate instantiations? Yes. So someone's saying, I assume by managing code bloat, you mean you'll address the potential problem where these auto-generated matrix types could start generating every possible combination of elements. No, not that exactly, because the compiler doesn't know whether you want that or not. I mean, that's a thing where you can manage that yourself. So in this matrix type, right, maybe I decide, you know what, if we're pretty close to a full matrix, if we only have 1 or 2 elements that are 0, then let's round up and give you a full matrix, right? If you want to economize on types, you can do that when you construct this. Because like I said, you can change these values. As long as you change them before you return from body text, you'll set them in the types. You could actually increase the dimensions in here. You could do whatever. So you could fill in the mask to get a more general type so that you generate fewer things. In fact, if you watch the demo, I'm pretty sure you saw this one, but the demo where I originally showed stuff like modify and body text, in order to cut down combinatorics, we were rounding integer types up to certain sizes, right? However, there's other things like, you know, suppose, you know what, I'm just going to get into it later, but let's just say that sometimes you know things about a family of types and might be able to write a procedure that operates on anybody of that family of types without having to actually specialize that procedure per each guy that you pass it, right? So for example, you know, when I generate matrix, we always have, let's go to this, right? We always have some array of floats, and then we always have an indices array that doesn't take storage and whatever, right? So you could write a procedure that well, with matrix, it's a little hard. Because I'm having trouble coming up with a real example. But if, for example, you just needed to know that something was an array of floats, that's an invariant of all matrices. So you wouldn't need to specialize your function for that. How long the array is, you would, right? Now with other types of data structures, that becomes more practical. So something like a hash table, maybe you have a number of elements in a hash table that don't depend at all on what the type is that you're hashing, right? But then some other things do change depending on what you're hashing. So for something like that, you might be able to write some procedures that operate on a subset of the type. But I'm getting ahead of myself. That's for next time, if it works. What if I want to write an array initializer for an array of structs? So struct types could be ambiguous. Yeah, I think if you want an array of structs, you're going to have to write the type. The typeless ones are just for things that could be easily inferred, like literals, right? Like integers and floats and whatever. The same kinds of things that you could write. You know, if you could say, you know, x is defined as whatever, the same thing will work there. Will I be able to apply this to operator overloads, for example? We haven't done operator overloads yet, which I forgot to mention, but you know, a lot of people would want to be able to just say times between two matrices to mean matrix multiplication. When we do that, which is probably going to happen, operators are just going to be desugared of functions. So everything that you see will work on all that stuff, right? There's no difference between operators and functions. Could a matrix be defined to contain anything like structs, where operations like multiplying matrices moves the structs around in the, yeah, I mean, this is just a struct. A matrix isn't a type in the language, right? A matrix is just a name for a kind of struct that I defined as the user. So of course I can put anything in here, right? I can put a GL bitmap in here if I want, it doesn't matter. I don't know, Casey is requesting some very serious power that I may not be able to deliver. That's all I can say. Only certain magnitudes of things are within my means. Even though apparently it is not that hard to do much better than languages like C++ at some of these things, yet there are some things beyond my language skills. So, okay, is this indices array stored in each matrix instance, or is it static in the type itself? It's basically, so this colon here, the first colon means I'm defining it. The second one means it's constant. When you have a constant member in a struct, it's like a static in C++. So it is namespace within the struct, but the storage of this is global, right? It is not stored inside the struct. And I demonstrated that actually, because if you remember, we did this thing where we checked the size of a foo. Where is that? Oh, did I comment out the whole thing? I commented out the whole size of the foo. Oh no, place test says size of foo is 16 here, right? But foo had one of these array literals, right? If the storage for this were in the struct in any way whatsoever, or even a pointer to this array were in the struct, you would have more than 16 bytes because these floats already take 16, right? Or this array already takes 16, but no, it takes no storage at all, except globally, right? Oh, n is the number of dimensions. Why is that not a size? Because, I mean, a signed 64-bit number, if you want a matrix with more dimensions than the size of a signed 64-bit number, then this library is not for you. That is a really big matrix. That is a matrix that will make your computer explode. I'm sorry. I explained place earlier in the video, so you could just go to the recording later and look back if you want an explanation of that. What about function pointers? Could they be with that? Could they be what? I don't understand the function pointer question. When this metaprogram is compiled, does the compiler know about other structs defined by the user? They just get mixed into the same program. So when I go over here, this file is not a separate program. This is just a debugging log of the strings that got added to your program that is presented to you so that you can understand what your metaprogram is outputting. And so that, when the debugger wants to show you where the breakpoint is or whatever, that it can show you some text that makes sense, right? But these didn't all get added as one file. They got added one chunk at a time. Remember, I had a body text that generated this, and the one that generated this. These streamed into my program one chunk at a time. If you're confused about how that works, I've demoed it several times in the past, and you can watch some of those older demos to see what happens. Am I very familiar with MATLAB? I've hardly ever used MATLAB. So the thing that I've heard about MATLAB is it's actually really terrible for doing math in because it's very loosely typed. So it's very easy to make a mistake and just get spam as a result and not understand what the hell is happening. So this would be a much more strongly typed alternative. In a system like this, you would know immediately when you made a problem. Now, in theory, that's true of C++, for example, but C++ is so ugly and hard to use that I think most people don't want to use it if they're more interested in math than programming, right? I would love it if this were useful to people in that domain, but I can't speak to that directly since it's not my domain, right? I'm very interested in programming, and so my concern from day to day in my job is programming. But I definitely am striving to build a design that's very user-friendly to the programmer and is very easy to understand what is happening in your program. And so if that makes it useful to people and the kind of people who use MATLAB all the time, then I'm all for it. Can the user manually specialize? Well, that's what, oh, you mean type this and then this and fill it out yourself? You can't right now. Except that a body text is a way of manually specializing, right? That's the way that you do that right now. If there were a reason to use this exact syntax, we could talk about that feature. I haven't thought of any use for that. It seems scary to me, actually. But, How does place work with SOA? If I have two int32s and place an int64 on top of them, will the SOA functionality fail silently, compile time error, something else? I haven't really put in user-friendly checking for place yet, simply because it's an experimental feature that I'm not sure if that's how it's going to go. I literally just did it so that I could have two ways of interacting with my matrix elements. What do I think about that? I think you would either get a warning or a hard error if you did that. I'm not sure. I would have to look at like how that happens in practice. Yeah, that's the thing. If you have a syntax that's more like the C union syntax, then you don't really have the same problem because you just treat that subunion as one element in the SOA, right? But when you use place, that's not a well-defined construct. So yeah, I don't know. It's a good question. Am I interested in developing features for better handling of different endianness? I don't believe that endianness should make it very far in your program, right? There's a very small number of sites in a program that should care what endian you're in, ever, 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 ever. And I think it's usually bad programming. Either it's bad programming or you're optimizing the hell out of a lot of things, right? If it's the former, I don't really want to enable that, right? If it's the latter, if it's actually useful to have little endian, big endian types, then we could look at that. I don't really know what that's useful for, honestly. But but I could talk to my optimization friends and see if they think of any ideas. It doesn't strike me as a high priority feature now. Someone says, you may have already answered this, but how do you prevent the same code from being generated over and over in different modules? Say using vectors of a certain length in several modules, is there a way to know? So you're making an assumption, which is that there are modules the same way that there are in C and C++, where they're separate compilation units. That is not true here, right? What happens is your modules get mixed together at a much earlier time, so the compiler knows that they're instantiating the same types, right? So you don't ever have duplication at all, so you don't need to deduplicate these things because they're never duplicate. So all these weird issues about pre-compiled libraries and how do I link to the right one with the right options that I'm trying to link my frickin' client program with all go away, because your libraries are stored, even if they're in pre-compiled form, they're pre-compiled only to an extent that makes them easier to redigest, but that doesn't bake in all this stuff, right? So if you make fewer, if the language design makes fewer problems for itself, then it has many fewer problems to solve, which then makes the language itself much simpler, right? So we don't have all these compilation unit problems that other languages have. Am I correct in assuming that polymorphic functions like length will play nicely with functions that are implemented for specific types, say a length function for a string? So far, I've just punted on that because I haven't wanted to deal with it yet. So right now, you can have overloading or polymorphism, but not both. But really, the compiler ought to be able to check to see if the polymorphisms overlap and only complain then. I just haven't done that work, you know. Maybe there's a theoretical problem with that, but I don't think so, right? Especially once you're using this notation like something slash matrix or whatever, it's easy to know that that's not a string. So, well, matrix add is not the right thing, but let's take length, right? Length is a highly, so if you have length of a vector, it's easy to know that that's not a string, even though this is polymorphic. So yeah, we should be able to disambiguate those cases just fine, but we'll see. It's just something that it's much lower on the list of feature priorities. Am I hiring someone to assist me with the compiler? Yes, but I haven't really found anyone yet. I mean, a lot of the emails I haven't looked at too closely, but I think this is the email, right? Is this right, people? I haven't typed this in a long time, but if you want to apply for a job, it's email here. However, don't apply for this job if you're a young, enthusiastic programmer who has some ideas but hasn't done this kind of work before. Ideally, I want either someone who's very experienced at low-level compiler stuff, right? Like not like writing scheme interpreters, or very serious video game stuff and can pick up compiler stuff pretty easily. Either one of those domains, and by very serious, I mean you write engines or optimize engines, right? Because that's the level of expertise that we need to bring to bear on this problem while we have a small number of people. So, you know, if you're earlier in your level of experience, it's not to be negative about that. Everybody goes through a big spectrum, but this is not a beginner level job. This is not even an intermediate level job. This is a senior, serious developer, advanced, hardcore programmer kind of job. So if you want to do that, email me here and we can talk. Can syntax tree modifications generate a debug file like the body text one? I've thought about that. I don't think there's any reason why not. I don't know how close it would look to source code, but it's pretty easy to convert it back to something that is kind of human observable, right? And so I think we will want that eventually, just hasn't been done. Can I generate code on runtime like based on user input? Well, if you link the compiler as a library and then output a DLL and link the DLL, yes. But no, this is not a JITted language. I think JITted languages are annoying and introduce a lot of complexity for no reason. part of what I'm trying to do with the design of this language is stay out of all these tar pits that other people wander into, because everyone's like, oh my God, programming languages are so complicated, but you made them complicated by doing all this stuff, right? So insisting on running in bytecode and then jitting yourself is crazy amounts of complication to get speed that you already had before you did any of that when you were just compiling native code, right? In fact, you had more speed when you were compiling native code. So just go back to that. Get rid of the bytecode at runtime and the JIT garbage and have a real compiler, is what I think. Can I give you shaving advice? Obviously not. I don't shave unless I have to. Is there any way to do something like template specialization in C++? I suppose you could just have if statements in the body text. I don't know what, I'm not fully up on my C++ template jargon because I abandoned the language, the advanced parts of the later, not advanced, but the more complicated new parts of the language a long time ago. I don't know exactly what template specialization means. If you mean like a const expert to do different stuff, then yeah, you would use body text for that or modify for that. One thing that's going to happen later is you're going to be allowed to use body text just for pieces of a struct. Right now it has to output the whole struct. But you're going to be able to have some of the struct just there and then have a body text routine that generates further stuff. Could what we are demoing tonight be achieved with the metaprogramming stuff from last time? Code gen by manipulating strings is great, but for bigger code gen is nice. It probably could be done but with what we had last time, or with some small extensions to that. However, here's what I think. I think you want both systems because they're both useful for different things. I don't think I would want to implement matrix math using the kind of metaprogramming that I demoed last time, just because it's harder to localize. It's a thing that operates on your entire program abstractly from this big system that runs at compile time, and it doesn't feel as light and easy to me. Maybe it is. Maybe it's the better way to do it. I don't actually know because we haven't done enough experimentations with this kind of functionality. But I'm operating from the premise that, look, sometimes I just want to be able to make a hash table of a particular type, and I don't want to need a big engine running outside my compiler to do that. I just want to be able to do that, right? However, you should have the flexibility to do it either way, right? So that's what I think about that. How am I handling aliasing? Is there going to be a restrict keyword? Has not been thought about yet. You'll notice that I'm returning all these vectors and matrices by value right now. I'm assuming that I'm going to be able to find a way to make that good or mostly good, which may reduce aliasing, may not. Anyway, we'll see. We'll see. At the very worst, if aliasing is only exactly as it is in C right now, except maybe a little bit better because we had some forethought about it when designing the language, that's still fine because, at least for version 1 of the language, just because, you know, aliasing is an optimization thing. It's not an expressivity thing. And, you know, usually like compiler writers get all up in arms about aliasing, but I don't think it's the biggest, I don't think it's on the top 10 list of what I, as a game programmer, wish I had to make my code faster, right? What I wish was that I could write code faster, because then I could spend more time optimizing it, because my optimizations are going to be way better than the compilers, because mine are algorithmic, and mine involve rewriting my systems to newer things that are better that I didn't understand the way I wrote them the first time, right? If I could write code 20% faster, then I have 20% more time to do that, right? And then maybe my code is less, if my code is 20% less complicated anyway, then the newer version is smaller anyway, so I get another gain there, right? So that I think is a huge boon. So whereas it would be nice to do something about aliasing if we figure out something to do, I'm not actually as worried about that as some people might be. Like aliasing is in vogue to care about right now. I don't necessarily care about it as much. How long have I been working on this? By calendar, it's been a year and 5 months or something. However, I took a bunch of time off 4 or 5 months. So it's been maybe a year of part-time work while I was working on the witness. I don't know. I'd have to really look at. I never made a GitHub style check-in calendar, so I don't exactly know. Wow, the questions stopped coming for a while. I'm not seeing any other highlight questions. If you're saying Q colon, I'm not Casey and don't have that filter, so I don't see those. After type parameters, will I be tackling universal function call syntax? Possibly not. You'll notice I don't have dot calls at all, and maybe I'll keep it that way. Like, why does everyone want dot calls? I'm not convinced it's a very good idea. What I will start tackling is namespacing generally, because right now, when I import modules, they all get dumped into the global namespace, and that's infeasible. So my question about namespacing is, how do you do it in a way that keeps things neat, but also isn't just annoying and doesn't make you type more than you want to, right? So I think you're going to have the option to dump things into the global namespace if you want, very easily, but then also compartmentalize them if you want. So that's the next thing. Like dot calls is so far down the list, I may not even get to them. I may not even get to seriously thinking about them before making the language publicly available because like, yeah. Does this use SIMD? I was going to put in some SIMD intrinsics on a lark, but I haven't yet. It'll be supported. Can we get some Go Bananas goodness? Oh, I already did Go Bananas, and if I run it now, I get a content warning in YouTube because I use licensed music, so I don't want to do that. I'm going to use this to make a game, possibly not the next big game, because it takes a long time to build all the structure you really need, but we may build a lighter, lower demand game, like something that doesn't tax the computer as much. So then you don't need as much optimization on the back end, and then use that to make sure the language is good, and then work our way up in terms of how complex are the things we make. My question regarding endian features was mainly about those parts of code that have if-defs or other mechanisms. So all that H to N and N to H is a totally botched C API, right? When you're sending and receiving network packets, there is no reason at all for you to care what network byte order is as a user. That is a giant botch, right? So usually the right answer is don't make that your API, right? Beyond that, I don't know. We have to see. I just have to see if there's a use for caring what endian things are. I mean, I think for sure there should be a flag that you can check, like a constant flag in the global namespace that says, am I big endian or not, right? Just so that you don't have to write some dumb thing where you like put a number into memory and read it back to know what endian you're on or something. But apart from that, I don't know. What are the big features I have not started? Someone's asking. Well, besides type parameters, incremental compilation, because you're going to need big programs, right? Namespacing. That's kind of it. Like, honestly, the polymorphic structs is sort of the last thing that could be scary, and so far I'm finding it not to be scary at all, right? Now, after all the big features are in, there's going to be a lot of like massaging them together to make the best thing and changing them around and stuff. Like I put a substantial amount of work this week or last weekend into redoing modify and body text so that they're less weird and more functional than, or more utilitarian than what they were the first time I introduced them, right? That they're less verbose and all that. And I'm going to keep improving things. So notes, I'm going to do structured notes. As opposed to the string notes that I did last time, when you put notes on struct members and can read those back at runtime, because, not just because it helps you put more complicated things there more easily, but also because otherwise you have namespace conflict problems. Like if I put a note called foo, how do I know that my library doesn't interpret foo as meaning something, right? Whereas if you use structs, you can see if it's your struct or their struct. So stuff like that, there's going to be revisions of a lot of features before the language is done. we'll see. I mean, I'm just going to keep working on it until it starts to stabilize. Yes, this should work on multiple platforms. It should work on at least Linux and Windows when released or shortly after release. I mean, I might just say screw it. I don't have time to go make it work on Linux again, but maybe one of the early contributors can do that. Whatever, we'll see. Any gameplay ideas I got specifically due to building this compiler? No, not really. All right, thank you everybody for coming by. I'm going to hang out in the chat on text, again, because I'm horrible at voice management. I need to learn to speak more relaxedly. I'm horrible at voice management, so I'm all tense and hoarse and whatever. But thank you for coming by. This will be on YouTube eventually. And I'm going to hope to do another demo. This one was kind of breakneck. Like I was working hard on features for 2 weeks. So the next one might be a month from now because that seems to be the more regular pace that makes sense for these. But I wanted to get a quick one in this time because this was going really well and I just wanted to show it. So thanks everybody for coming by. And next time we'll have more with polymorphic structs unless I do something different randomly.